All right. Okay, so welcome to class 7. I am going to have a little introduction of what we covered last time, just to set the field. So otherwise, if I start with something that you have already forgotten, then um, then we will have a problem. So this is what we want to solve. We want to solve the problem of the potential distribution in the Dirichlet rectangle, which is basically the solution of this equation. This is what we want to solve, that equation we want to solve, given that we have certain boundary conditions. So as we said, we put voltage equals to 1 at the top and voltage equals to 0 grounded at the bottom. At the bottom and the side. So, oh, the ground is already there. So, um, bottom and sides are grounded. All right. The way we derive these things is we said we are going to put some cheating functions. We're going to cheat. We are admitting that we're going to cheat. And it can be demonstrated mathematically, which I will not do. It's a crazy derivation. That if we put these functions, which are the shape functions, the shape of the triangle functions, if you minimize, if you do this integral, you get to the solution. And the real way we're going to do it is in a 2D way. So this is what we're really going to do. Um, and this is for internal nodes. Okay, we have derived, after pages of triangle manipulations, that coordinates and things, we have derived the shape functions. And the shape functions are these things, this phi, I would probably should put phi 1, phi 2, phi 3, just to say that they are different. And they are functions of P, Q, and R. P, Q, and R by themselves are functions of the coordinates of the triangle vertices. So what we really have here is a big mess of mathematical manipulation, but in the end, it's all simple and it's all related to the triangles. Okay, so the other thing that we need to remember is the ones that we apply Gauss law and we remove all the external the boundaries, we are ended up with this equation. So this equation is the equation that we need to solve. And what we need to compute is VA, right? That this is what we need to compute, VA. So we know these shape functions, and what we need to take is two gradients. So this is gradient 1. This is the other gradient. So, and do the dot product of those two gradients, and then integrate with the area. At the end, none of these things is going to be function of the x, y, and z. So the area is going to be the area of the triangle. I will just multiply by the area of the triangle. So let's start by taking the gradient of a move it. The gradient of the VA. What is VA? Remember, VA is the assumption that we make, is the initial condition, if you want to say. It's the initial condition or the initial guess. So VA is the initial guess. So we invent a solution and we say this is the solution, and we compute this thing and we ended up with the residual. And if we make the residual, and if we compute this shape functions to reduce the residual, then we are okay.
Sorry, Professor.
Yeah.
So this equation is known and the WK is already known. So
No. Well,
it's known. Do we know the shape function? No.
we know the shape functions. Look at them here.
Yeah, but the WK is shape function, right?
WK is a shape function, which here is those phi's. Yes.
So you have another initial guess. So everything in the equation we have already known.
No, because what you want is to compute VA. You want to compute a let's say that you put VA here. You invent a VA. You put it here. It's not gonna meet the equation. So what you need is to compute a new VA. Let's say a new V. So if you see, for example, the shape functions are a function of voltage 1, voltage 2, voltage 3. So those are the ones we want to compute. The potential at the vertices. Okay. All right. Okay, so let's do this operation. Let's do this operation. So the gradient of BA is going to be, well, the gradient of so you need to put VA. What is VA? Give me a second.
Yeah.
Okay. So let's say VA is equals to a whatever function VA. Oops. Say the VA is a function of X, Y, and Z. All right. And I need to compute the gradient. So what I'm going to have is d dx BA of X and Y. I am just not, I am not going to take the Z. The Z, since I'm doing it in 2D, I am going to say there is no C. So the gradient is this one in direction X. Let me put it in the same color. So this one in direction X plus d dy VA X and Y in the direction Y. So that is what that gradient is. Now, if you say what would be VA? VA of X and Y and Z. I'm gonna have to move this guy down a bit. Right there. Okay. BA of X and Y is going to be the sum. Remember the linear interpolation. I don't have it here, but it's the linear interpolation 1/2 area of QIX from I equals 1 to 3 plus R1 or RI. This is RI Y plus P plus PI. And all this multiplies VI. Well, all right. VI, I'm going to change it here. VI, these are the potential at the vertices. Okay. These are these Q's that we computed that are Q's, R's, and P's, which depend on the triangle. triangle functions of the triangle shape or triangle vertices too. These are the interpolation, let me change it. These are the interpolating functions or the interpolating coefficients. Yeah, remember that for a triangle we had that any point, let's say this is 1, 2, 3 vertices, and we want to compute this thing, or if we want to compute the potential inside anything, we need to use an interpolating function like this. So at any internal point, and we can write a for any internal point, the potential of any internal point depends on the potential of the vertices and the interpolating function. This is just like if you were to write y equals to ax plus b. So this will be your q, and this is your p. But because it's in two dimensions, it's not in a line, then we need an additional parameter. So, but that's what these things are. So let's take this gradient of this function, and I am going to tear this page. Let me push it down. Add space, drag a lot of space. Let's say there. So now I'm going to compute. I'm going to substitute this. Oops, this guy here and there. So the gradient of BA is going to be, since I have to take only the derivative with respect to x, right? That's all I need to take. So this is going to be 1 by 2a q I. I need to add it. QI. Let me expand the sum right away. So it's going to be Q1 x. Then the rest of the things are constant. It doesn't depend on x. So I just have to forget about it, right? And this will be plus Q2x plus Q3x, and this multiplies B. This multiplies what? Nothing. It multiplies. That's it. It multiplies. No, it multiplies BI. Multiplies B.
The gradient with respect to what?
The gradient? Well,
With respect to what?
no, with respect to x. So the gradient is the gradient. You define the gradient like this, right? Gradient of a function. Let's say b. It doesn't want to erase. So the gradient of a function b. The gradient. Come on. The gradient of b is a vector, right? That has ddx of b in direction x plus dy of b in direction y plus the c component, which I don't have it. So this is what we need to do. So just take the partial derivative of this equation. So the functions, this is not a function of x. It doesn't exist in the first term. This is not a function of x. It doesn't exist in the first term. So I have only the sum of q1 x. But when I take the derivative, I remove the x. Yes, so it's q1 plus q2 plus a q q3 q3 b1 bi. No, b no. Q1V1 plus Q2V2 plus Q3V3. This is in the direction X. Plus 1 by 2A. Now I have R. R1, let me make the R better. R1V1 plus R2V2 plus R3V3 in direction Y. Okay? So for this equation, I have computed this value. Now I need to compute the other one, the gradient of the shape functions. Okay? So I have here the gradient of the shape functions. Let me put a very vivid red. Okay, that would do. So the gradient of the shape functions is going to be basically is the same thing, right? It's the same thing. So I have the derivative of, let's say, the shape function 1. The gradient of shape function 1, which is this one here. Let me see if I can steal it. No, it doesn't work. So I'm going to make it smaller so that I can simply copy it here. So is going to be the gradient of 1 by 2A P1 Q1 1 by 2A. It's the same thing. Q1X plus R1Y plus P1 V1. And if I continue, so instead, this is not going to be, it's just going to be the function. It's going to be continue plus a, yeah, there will be the derivative with respect to X of that plus the derivative with respect to Y, and this will be in direction X, plus the derivative or with respect to Y. No, it's all the way. Sorry. I am going to have to copy this function entirely here. Copy, otherwise I won't be able to see it. I'll make it smaller so that I can have space. All right. Let me even delete everything here and do it correctly. Okay. So shape function 1. Shape function 1 is equals to 1 by 2a P1 plus Q1x plus R1y V1. And I take the gradient of this. Gradient of phi 1 is going to be 1 by 2a. And I'm going to have Q1 V1. That's it. That's with respect to x. There will be ax. Plus, with respect to y, I will still have 2a R1, then y disappears. R1, B1, AY, and I don't do the C. So now the gradient of phi 2 is going to be 2A. It's basically the same. Q2V1 in direction X plus R1, it would be B2, not B1. B2, R1, R2, V2, R2, V2 in direction Y. And the last one, the gradient of function 3 was going to be 1 by 2A, Q3, V3, and this is direction Y. Direction X, no, this is direction X, that was correct. Q3, V3 in direction X plus R3, V3 in direction Y. And now I can delete this guy here. All right. Now, I need to do the dot product of this thing, this gradient, and I need to build all these gradients, right? So let me get the gradient of the shape function will be 1 by 2A. I am going to have AX plus 1 by 2A, AY, right? And I will have in AX, I will have Q1 B1 plus Q2 V2 plus Q3 V3. And I will have a no, I need to add them vertically like that. So I will have Q1 B1 plus Q2 V2 plus Q3 V3. And that is all in direction X. For direction Y, I will have R1 V1 plus R2 V2 plus R3 V3. So I just, the Y is here, so I just add them here. All right, so that's the gradient of the shape functions that I need to do dot product with this thing, right? So I need to do gradient of BA dot product gradient of shape functions. So the dot product is going to be the multiplication of whatever I have here in the direction X with whatever I have here in the direction X. Okay? So I'm going to multiply, let me see, that with that. So
Why is the dot product?
this came from Gauss' law.
You didn't finish the delta VA yet.
What do you mean? This is the gradient of VA is finished. I don't want the Z component. It just
No, Dylan. You only finished, so VA equals 1 over 2A times the assumption. No, the upper with the green equation. VA equals 1 over 2A.
First line, right?
this line.
Upper the green one. No,
Yeah.
VA bracket X comma Y.
This component is here, and this component is here.
Yes, but with VA, there is a VI at the end. So when you do the derivative, you need to also do a derivative of VI.
No, what not VI is V1, V2, V3. It's a constant. This is a constant. This is the potential at the vertex. So it's just a constant.
Okay.
So so I have here, and this is the function, right? So that and that are constants. And the only thing that you take the derivative is x. So x disappears. That's all I do. Disappear the x. But I cannot modify the product. Okay? So now I'm going to do the dot product, but for that, I'm going to steal this guy. Copy. I am going to put it here. Paste so that I can see the dot product. The dot product is going to be just multiplication of the x direction with the x direction, right? So it's 1 by 4a squared. It's all the same, right? So Q1V1 plus Q2V2 plus Q3V3 squared. Yeah. And the second, this is plus the same factor, 4a squared, and it's going to be the same way with R's. R1V1 plus R2V2 plus R3V3 square. And now I can delete this thing. Can delete this thing. Okay. All right. Very good. Now let's somehow I don't like that it's a square, but it's exactly the same thing, eh? It came to be the same thing. Everything is exactly the same. So Q1, V1. Something is not right.
Information.
Oh no, it cannot. It is because I cannot have the voltages square. That's my concern here is I cannot have the voltages square. So, because otherwise I have to solve a quadratic function. No, the shape functions shouldn't have the voltage. That's the thing. The shape functions don't have the voltage, so I needed to delete from the shape functions this thing, right? It's so the shape function doesn't include the voltages. So the voltages are there, but that's for the this is for the potential, but the shape function itself doesn't have the voltages. So that's where the problem here is. So I need to remove, oops. I need to remove that, 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 that. Oh, no, this is the voltage. This is fine. What I need to remove the voltage is here. This is the shape function. And I need to remove it from here, and from here, from here, and from here, from here, here. And that's it. Okay, now, so the things are going to change. So shape functions don't have this, don't have this voltage, doesn't have this voltage. It doesn't have the voltage, it doesn't have the voltage, it doesn't have the voltage. Okay, now I need to erase all this. Okay, now it's all right. Equals to 1 by 2a over a squared. And I will have is q1 plus q2 plus q3 and multiply all this, right? This thing in direction x multiplies the direction x here, which is q1 v1 plus q2 v2 plus q3 v3. So it's q1 v1 plus q2 v2 plus q3 v3. Okay, plus the same thing. 1 by 4a squared of R1 plus R2 plus R3 that multiplies R1 V1 plus R2 V2 plus R3 V3. All right. So I have to just write this as a when I do the integral, the area integral of gradient of VA gradient of function dA, the only thing I need to do is this will be whatever the function is multiplied by a. So this integral will give me 1 by 4a, no square any longer, and it's going to give me something that is function of b1 plus something that is function v1, function that is function of b2, plus something that is function of b3. And remember, this is going to be equals to 0 for internal nodes. Okay, so it's going to be q1 plus q2 plus q3 that multiplies q1 for v1. For v2 is going to be no, I need to add more. I am going to call this to simplify it. This is going to be Q simply, and this is going to be R. So it's going to be Q1 plus R1, V1. And this is the other is going to be Q2 plus R2. And this is going to be UQ3 plus R3. Okay, so that is the final equation, right? So if I were to put this in a matrix, V1, V2, V3 equals to 0 for internal nodes. This is internal nodes. So I will have to put here Q1 plus R1. Okay, I can separate this. So I think I can separate. Instead of Q1, I can put Q1. So remember, Q is Q1 plus Q2 plus Q3. So I need to do one more step. I need to separate this and rearrange it in a different way. Yeah. So let me write it in a different way. Only erase this thing. And from here, I am going to steal this one. Copy. I am going to put it, arrange it in a different way to make it simpler. So what I really want to do is to write a matrix where I will have V1, V2, V3 equals to 0 because this is an internal node. And this matrix needs to have all the components of this equation. So see, if I multiply this by this, I will get Q1, Q1. And then the same, if I multiply this by this, I will get plus R1, R1. Okay. Now, I can also multiply that by this. So I will get Q1, Q2 plus R1, R2 is a function of V2. And I do the same. Then I get Q1, Q3 plus R1, R3. Okay, so I have already made the multiplications of the first term in here. Now let's do the second term. So now I'm going to do this one times this one. Okay, so it's going to be Q2, Q1 plus R2, no, R2, R1, R2, R1, and then I continue, and it will be Q2, 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 Q2 plus R2, R2 plus Q2, 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 Q3 plus R2, R3. And then I do the last one. And you see the matrix is building by itself. Yeah. So now I do the last one with, let me do what color. I'm going to do orange. So I do the last one. I do Q3, Q3, Q1. So here is going to be with orange. Q3, Q1 plus R3, R1. And I can simply just write it because it's it just follows, right? Q3, Q2 plus Q3, R3, R3, R2 plus Q3, Q3 plus R3, R3. Okay. Of course, it's a big, big mess because the Q's are function of the functions of the functions of the functions of the parameters. But all the calculations is nothing but additions and multiplications. There's nothing else. So, okay. Now, I do a final change of variable because this will be just too horrible to deal with. So the number, the value I use is the E. This will be E11 for triangle K, because this is for each triangle, right? And it would be E12 for triangle K, and E13 for triangle K, which will multiply voltage 1, voltage 2, voltage 3, equals to 0. And then this will be E of triangle E21 of triangle K. This will be E22 of triangle K, E23 of triangle K, and E31 of triangle K, E32 of triangle K, and E33 of triangle K. Okay, K is the triangle number. Okay, because now what I need to do is I need to put it all together. I went triangle by triangle by triangle, but what I want is to bring the whole thing together. So let me copy again this thing. Come on. Copy. And I'm going to put it here. Paste. So I put 0 for internal triangle. So for 0 is for internal triangles. When they are not internal, let's say, let's talk about triangle 1 is not a good one. Let me put number of triangle. The number of the triangle, I'm going to put it with blue or with something. Let's talk about triangle. Let me number them. So this is triangle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And, oh, somehow I have put it, that was the node. 16. Okay. And for my example is going to be now triangle 16. This one, let me put it in red, very red. Triangle 16, I extract triangle 16 over here just to be able to things here. So this is triangle 16. And it has node 17, node 10, and node 18. Okay. Now, for node 17 has specified voltage equals to 0 because it is on the edge, right? And triangle, and the other two nodes are internal nodes. So if I were to build the elements corresponding to triangle, let me go all the way to the edge. All right, equals over here. And this one, I'm going to push it over here. Okay. So triangle 1 will have already specified the value. So but triangle 16, let's say here, this is 16. So 16, no, node 16, this will be, this is the nodes, not the triangles. These are the nodes. I don't need to solve for node 1, 2, 3, 4, 5, 6, 7, 8 because I know them. I don't need to solve for node 9, but I need to solve for node 10. So at some point, I will have node 10. Node 10 could actually be the first one I need to solve. So probably will be here, voltage 10 will be the one at the top, right? Then there will be voltage 17 over here, which is not because it's zero. So, and it will be voltage 18. So, and I need to build for the vertices this matrix, right? This matrix, I need to put it for the vertices. So, V1 is 0, so I don't do that. I only do a 10. Let's do 10. So for triangle 10, for triangle 16 that has node 10 that needs to be computed, the potential in node 10 needs to be computed. So let me see. B1 was a 17, so this will be B17. This will be B17. This would be V, no, this will be B10. This one would be B10. This would be B17, which is known. It's okay. And this would be B18. So for B10, I will have E11 of triangle 16. Then for B17, I don't need to do anything. It will be here somewhere on the right-hand side. And then I need to go for B18, it will be E23 E23 of triangle 16. And that's all I need for that line. Then over here, I will have E33 of triangle 16. And we'll have triangle 18. No. Yes, this is correct. E33 of triangle 16. And we'll have here E31 of triangle 16. And this is only for triangle 16. The 17 doesn't, the node 17 doesn't count because it's known. So its voltage is going to be 0. So I don't need to compute it. But I need to compute the one from here and from here. In fact, somewhere here, it will be E12 of 16 times 0 times 0. So there will be an entry 0 here that corresponds to that because it's 0. For some other nodes, for example, if I were to take node 2, that would not be 0. That will have whatever triangle is touching there, will have to have a, let's say, triangle 1. Let's say triangle 1. Triangle 1. E 1, 2. E12 multiplied by 1. Okay, that would be there in whenever I have to compute something for triangle 2. Triangle 1 has everything specified. So this is not be, it will not be triangle 1. Everything is specified, it will not show there. But for triangle 2, I need to compute this value, right? So it will come over here. It will come over here. E22 of triangle 2 will come here. Plus. Okay. I don't know how confused you are, but
Internal,
very confused, right?
initially you are assuming internal nodes is a zero.
Internal nodes equals to 0. But if the triangle touches an internal and external node, something is going to come into the independent variable. Something is going to come here, right? So let's say it will be zeros. Let me put it here big. This will have 0, 0, 0, zeros for internal nodes, or yeah, let's call them nodes. But it will have some value, probably negative of the e's, multiplied by 1, because this is the voltage, right? Voltage excitation. E1 is all this crazy thing. E1 will be this. E11. So these two matrices are the same, right? These two matrices. I just make another one last. I cannot carry Q1, Q1 plus R1, R1, and then I need to make an equivalent. So what I have done is call this guy E11 for node K. Okay, for triangle K. So K is a triangle. K is triangle number. E11 is whatever is your triangle position 1, but it could be the vertex of the triangle. Let's say this is one for a given triangle. Let me see, what is the triangle? For a given triangle here. So I have this triangle. So I will have E triangle is 16, but it has no 17. So it will be 17, 17. Right? That's what this entry will be. But I have to take it from here. Whatever that value is. So I have to take it from here. This is for a K triangle, but I use, this is number 1 for, this is triangle number, this is vertex number 1, vertex number 2, vertex number 3. But in the generic formula, it could be something that is in between. So it could be this one, this black one, which is node 17, node 19. So overall, this would be node 19, this would be node 26 and node 27. So this would be 27 and this would be 26. Okay. For the particular triangle is 1, 2, 3, right? And it comes into this equation over here. For the overall, I have to change and I have to put whatever is the number of the actual number of the triangle. Yeah, the actual coordinates of the triangle. So each one of these Q's will have a different value here Let me put the purple. Each one of these Q's have a different value here than here than here. Yeah. So, and it all depends on the shape of the triangle, the coordinates of the triangle. I think everybody is very confused. Fayaz, how confused are you? 100%?
No, but the point is the matrix, where you are converting E's.
It's just an equivalent. So let me put it here. E111 will be Q1 plus R1. That's what it is. That's what this is. I'm not doing anything else. Just defining it. If you wish, let me define it like that.
So the superscript is
The triangle number.
defined.
Yes.
So it transfers to, let's suppose if it is E superscript.
You could say this is Q111, R11, R11. You could say so if you wanted. Yeah. So if you wanted to have an independent variable for each one of them, that's what you would do. Yeah. Now, remember, Q and R are a crazy combination of the coordinates of the triangle.
Some of the Q's are common.
Some of the Q's are common,
Some
yeah.
are
But you can always treat them independently. You can do triangle by triangle, and you add them. So in the end, you will have something like this, right? Let's say, let me actually even give you some elements on the other matrix, right? So you will have a matrix here.
If we reduce the matrix by eliminating some common ones, will it have some symmetry?
The size of the matrix is the number of nodes by the number of nodes internal. So the size of this matrix, which I'm putting here, is n internal times n internal. It's a square matrix, this one. This one is n internal times n internal. Here is only n internal and times 1, right? And here is n internal times 1. But the only thing that you have here is external. The external values. If it is internal, is 0. These are all internal here at 0. But all external are represented there, and there will be a function of some e's, and then the voltage known at node 3, for example, or in this case, a node 1, plus the voltage of node 3, depending, let's say, what triangle is. If it's a triangle on the top, right, let's say this triangle, the first one. This is 1, 2, the node, and this is, just to use the same number, is 9. So from the point of view of the entire system, this is node 1, this is node 2, and this is node 9. That's for the system. From the point of view of the triangle that is here, all right, so this is triangle 1, but the number will be 1, 2, 3 for this particular node. Now, we have to forget about the number of the triangle, the number of the vertices for the triangle, and use the general number. So we have to substitute. Oh, if this is 3 here, but it's 9, it's going to get an entry in 9. So this, let's say this somehow, that something is not specified, because this triangle number 1 doesn't appear anywhere. Yeah, because everything is known on triangle number 1. What is the triangle here? Triangle number 2 is better. Better to consider triangle number 2. Triangle number 2 will be here. Okay, and it has node 10. Now, from the point of view of, let me actually delete here. Let's put triangle number 3. These are, let me make it actually very big. This is node 1. This is node 2. This is node 9. And this is node 10, generic. And I'm going to put this triangle, which is triangle number 2. For triangle number 2, this is 1, this is 2, and this is 3. Yeah. From the point of view of the triangle number 2, that's what it is. But from the point of view of the general, we already know it. I mean, from the general, we have to use the numbers, the purple numbers. So, and the first variable that is going to appear here is V10. But on the right-hand side, on the first column, is going to be some E11 for triangle 2 that multiplies a B1, which is going to be equals to 1. But it's also going to have something to do with triangle 9. So it's going to have, let me put this, multiply by 1 plus triangle 1, variable 1, 2 of triangle 2 times 0. Okay, so this value here is voltage equals to 1, and this value here is voltage equals to 0. So because the voltage here is equals to 0, to 1, and the voltage here is equal to 0. So it's known. It doesn't, so I need to pass it to the right-hand side because it's known. You write the equation, and then, but I know this value. You put it to the right-hand side. Yeah.
So you're not writing the triangles with two vertex node.
This particular triangle, the one here at the corner, I am dealing now with this triangle here, right? This triangle has 2 of the nodes are known already. I need to compute the potential only in one of the nodes.
Yeah, so are you going to put the triangle 1 into the matrix?
You put it into the meshing, but you don't need it.
So triangle 1 is not in the matrix.
It, in the end, is not in the matrix, no. Because you know the values of both of them. Of all the potential of triangle 1, you know them. So they are on the right-hand side. So in the very end, is you need to solve AX equals to B. This is known. This is to be computed, known. And of course, this is the matrix.
But my question would be, if you were saying the second column of V1, V2, V3, that column, it's N1.
Which column? Which equation?
The lower one? Yeah, this one.
This one over here.
And so you're seeing the second part.
The right-hand side.
The left side.
All
the left hand side.
the left-hand side.
Yeah.
Okay.
So the size of the equation is number of nodes of internal times number of nodes of internal.
Yes.
And the next one will be number of nodes of internal
Times 1.
Yeah. So if only the triangle 1 is not considered, then the number of triangles must be larger than the number of nodes internal.
Okay, repeat that. So we only have, what we don't know is the potential at the internal nodes.
Yes.
So, and those are the ones that you're going to put here. This is potential at internal nodes. Here, you have functions of ease and the potential of boundaries. Okay. So you still have the triangle. You still have its coordinates because it affects here. It will affect here, right? Whatever shape it has. So it's triangle one is not in the um, in the matrix. It's not in the main matrix. Oops, I don't know what I did. Triangle one is not in the main matrix, but it is in the right-hand side. So you still need to put the triangle, compute the RQs, all of this craziness, and put it on the right-hand side, multiply by the potential that you have in there. In fact, this number will be a negative number, right? Here, it will be a negative because you're passing it from to the other side. Say, for example, here, since here you need to, because this is known, because big one is known, so you need to pass this one over here.
Like KVL.
Just like KVL. Yeah.
Yeah.
Yeah. So you already know that. So this is the data that you know. You cannot solve a matrix that where the right-hand side is all zeros. You need to have some excitation, right? And the excitation here is given by the boundaries. In some of the boundaries is 0, and some of the boundaries is 1, or whatever potential you put. Payas, how confused are you?
Now it's
100%?
no. Like you are saying that we have to add these numbers in the vector. Then
So let me put this equation. Let me copy this equation, put it below, and put the actual node 1, a triangle 2 here. Triangle 2. So let me copy this equation. Copy. Put it here. Paste. What?
But if your triangle is not on the boundary and it's on in the middle of your
then
An internal node, then you
Oh,
put
yeah, 0.
then all nine elements exist, and they are all equals to 0. So this is perfect for an internal node.
Yeah.
So it's the initial condition.
It's
What the internal
initial-
node, not initial condition. Internal node is like this.
So
Like
actually, we
initial condition for internal nodes. Like after that, they will change.
The ease will not change. This matrix is constant for as long as you don't remesh. This matrix is constant.
actually we are not
Like
transferring
how
the
the value
we are not transferring the values from left to the right. Actually, what we are doing, we know the values on the left-hand side, we are just writing them the values of there.
Exactly. Exactly.
negative. If
So-
we know, if we know just like this, if we know that there is a value here, which has.
Which you know, you just need to put it on the right-hand side.
Which I know when it multiplies with this,
Yes.
it gives me the value that I know, already know. This is the one that I know.
Yes.
When I multiply this, we are not
So-
transferring, we are just writing the multiplication of this here.
Yes, I am gonna do it for triangle 1, right? Here, I'm gonna do this for triangle 1. No, not for triangle 1, for triangle 2. Because triangle 1 doesn't show in the equation. So it's triangle 2. Triangle 2, triangle 2. 2, 2, 2, 2, 2, 2. All right. Triangle 2, where was it? Here. Triangle 2, it has no 9. So let's write it. Let's actually even leave it like this. I am going to put it exactly the way it would be. Would be node 1 for triangle 2 is no 9, right? So I will have E2 9 E2 9. Then I will have E2 E2. So I would say triangle 1 goes to 9, 1 goes to 9, 2 goes to 10, and 3 goes to 2. So these things here, let me actually move it here. And here, this is a triangle vertices. And this one is mesh nodes. Okay. Better, Fayas? All right. So 1 goes to 9, 2 goes to 10, so it will be 10. No, 1 is 9, 9, 10. It will be 9, 10. And then the other one will be 9, 9, 2. Okay, then E 2, 1. So is triangle 2. E 2 is 10 and 1 is 9, which should be, right?
Yeah.
So is there a question online? So somebody's talking. E22 is 10, 10, 2, and E1, E23 is 10, 2, 2. And here will be V9, V10, and V2 equals at this moment still to 0, 0, 0 at this moment. Then E31 will be E2, 9, and this will be E3 is 2, 10, number 2, and this will be E2, 2, 2. Okay, but I know that V9 is equals to 0, right? I know that V9 is equals to 0. V10 is to be computed, and V2 is equals to 1. That I already know. So I don't need to compute them. If I develop this equation, so E99 V9 plus E910 V10 plus E92 V2 is equal to 0. But because I already know this one and this one, so what I'm going to do is just leave E910 V10, which I need to compute, will be equals to the negative of E99 V9 minus E92 V2. All right. So that's for equation 1. For this row, I will have E1010 V10 equals to the negative of E109 V9 minus E102 V2. And the final will be E 210 B10 equals to the negative of E29 V9 minus E22 V2. Okay. And then if I want, I need to substitute the V9 is equals to 0 and V2 is equals to 1. So this will write to me these entries in the matrix, right? So is it better? Is it clearer now?
Yes.
Okay. So Kashif? Yeah. So, but I need to build the entire matrix because node, in this case, triangle 2 is not the only triangle connecting to node to node 10, right? I know this voltage, but I don't know here. But to node 10, I have 1, 2, 3, 4, 5, 6 triangles connected. So there will be six elements in the entire triangle, probably one, let's say 1, 2, 3, 4, 5. It will be not random completely, but they will be in a band. They will be in a band. Yeah. But in the band could be whatever, basically whatever, because let's say that you have a space like this. You could make the triangles like this, for example, right? You can make them like this, or you can make in any other way, right? So it depends on how the triangles are. The algorithm that does the discretization puts the triangles.
If does the triangle formation shape affects the symmetry of a matrix that you are going to form,
Uh,
or there is some.
it really doesn't matter. It really doesn't matter. The important things that from the point of view of the finite elements method, what is important is that you never have a degenerate triangle. Because the whole thing, all these elements, all of them are divided by 1 by area, right? All of them have all these Qs, they have 1 by area, right? Or even by area square. Area square, no, it's just the area. So somewhere, because this is just that, it's not the integral. When you have the area integral of this, then this disappears. So, but the area is always divided. So if you have a 0 area, that's it. Your matrix is gone. It automatically is singular, and that's it. You don't have any any solution, right? You have there an infinite number. So that's why you have to be very careful about the triangles. The better formed triangles, the better. This is much better than this. And of course, the worst thing will be that, right? The numerical accuracy and the convergence of these things, eventually it may not even converge if you have something like this. It can tell you that your matrix is ill-defined, ill-conditioned. So the programs will give you the condition number of the matrix. Yeah. And if the condition number is too large, you're done. Yeah, exactly. Okay. Now, other things that are important is the numbering of triangles, because the size of the band, and this is exactly, we are following naturally into what is next for me to describe, is what are the solutions methods for this. So the numbering of the triangles is very important because that determines the band. So you see, if you go here, 1, 2, 3, 4, 5, 6, 7, 8 on the first row, and then continue below, and then continue below 9, 10, 11, blah, 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 the band of the matrix is going to be 9, because there's no connection between 1 and 10, and there's no connection between node 1 and 11. So from that point on, everything is 0 for that particular row. So, all right. So that takes me to how this matrix is compound. So the final elements matrix. So first of all, the whole thing reduces to solving AX equals to V. That's it, right? How do we make the final elements matrix? First of all, has all these properties. Is diagonal dominant. So the dominant, the main diagonal is heavier than the others because there will be sums of more elements in the diagonal, right? Every triangle that touches a node adds numbers there. So it becomes heavier and heavier in the diagonal. It's very large. It has many zeros, so it's sparse. It's banded. It has a band. It's a band matrix. And very important, is symmetric. All this gives you a lot of, there are a lot of techniques on how to solve these things. So the solution method, so if, let me put the matrix. So it's something like this. It's very large, but it has a short band, right? The band is like this. So it has a band. The matrix could be, I don't know, 1,000, but the band is probably 30, right? So, and even in the band, there are a few numbers. So it's not like it's full. Not every row is full. It has just a few. Most of it is zero. Most of the matrix is zero. But important thing is that it has a band. So what are the solution methods? The solution methods are the one that is, I liked it for many years, but I don't like it any longer, is SOAR. Successive over relaxation. Successive over relaxation, SOAR. It's just a fancy name to say Gauss-Seidel. From the point of view of a final elements, we call it successive over relaxation. When you're solving this as a power flow, is Gauss-Seidel. So you're going to write the equation, right? What you do is you get the diagonal elements here, and you solve for them. So you put the matrix, you pass everything to the right, you have an initial guess, and only because it's diagonally heavy, it's perfect for Gauss-Seidel. So SORD is just an elegant name for Gauss-Seidel iterations. I don't like it any longer too much, but it's very easy to program. It's very easy to do. Of course, you can have the another solution method will be Gauss elimination. Gauss elimination will be great. Being symmetric, there are today some beautiful method techniques. Some called from the Krylov subspace. The Krylov subspace, in particularly GM-res. GM-res. Oh, that method is beautiful and applies beautiful for symmetrical. Since the matrix is symmetric, GMRES is perhaps the most efficient method there is for symmetrical sparse matrices. You don't even need to worry because the programs have them in themselves, and the MATLAB has them all. So if you want to learn more about it, how the Krylov subspace methods work is like this. You have to solve AX equals to B. So the way they do is they multiply this for an approximation of A minus 1. So start with that. And let's say approximation J. The very first approximation, A1 is going to be the inverse of the diagonal elements. A11, 1, A22, blah, 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 1 by A33. So sometimes this is called a preconditioner. But that's the theory. You multiply by a guess of the inverse. And the first guess is just get a diagonal element. And that will already approach you to the end. Then you compute a residual and come up with a new. So you're going to do AJ plus 1 minus 1. And then you multiply this plus A minus 1 J. And you multiply this with A minus 1 J minus 1 AX equals to B. So you only do matrix multiplication. So you can parallel this thing perfectly because matrix is row by column, row by column, row by column. So if you have a vector computer that does vector calculations, it becomes extremely fast. So what else? What other methods we have? The beauty of these things, but this thing is that is suitable for parallelization. None of the others are suitable for parallelization. Gauss idle or Gauss elimination, you can't. Now, the good thing about, for example, Gauss elimination is that if you're going to solve the same case again and again with changing excitation only, for example, you have a linear problem and the geometry is fixed. Your matrix is fixed. And then you can solve for 10 different excitations very efficiently. The others, no. The others, you need to go all and solve it again because it depends on the numbers. It depends on the numbers that you're computing. Not depends on the location and the fact that this is good. So this over relaxation, it will be great. It's great for not that one. Gauss elimination is great for fixed geometries. You know how many solution methods are in console, Fayaz? Can you open console and show me the methods that we have?
Arnoldi gradient.
What's that?
Arnoldi gradient.
I haven't seen it. No, in any I don't know what the advantages are of Arnoldi. Yeah.
Mostly it is used for eigenvalues.
Yeah. I haven't seen it, right? There are methods too for positive definite matrices. There are some methods, but I don't have a lot of experience with them. I have experience with whatever is used in power systems and whatever is used in finite elements. Other than that, the other methods I don't know. Okay. So while Fayaz is looking for which methods, let's say COMSOL methods, which I really don't know. Okay. No. When you have to when you click on solve,
Yes.
no, we look for it later. It doesn't it doesn't have to be today. I have more material to compute. Okay. So consider that we have computed b of x and y using FEM. So we know now the distribution of the potential at every location on that arrangement that we have. So we know that it's going to be something like this, like that. We know that. We know this potential. But that's not the most important thing that we need to compute. Okay, the potential is something good. But what we really want is to compute the electric field. E, the electric field. Okay, first of all, I think let me stop here. What we have computed with finite elements is not this thing. What we have computed is the voltages B I, so B at the vertices. So what we have considered that we have computed BI, so is the potential at vertices. That's all we have computed, right? We know here, here, everywhere, internal or external, whatever, we know this potential over there. What if you want to compute the potential in the middle, not at a node? Interpolation, right? So you go b of x and y, you're going to have to, let me put it on the other way. So interpolation. So you're going to have b of x and y. You need to take the triangle where you are. First of all, need to go and say, oh, I am in this point. I get this triangle, and I'm going to go voltage 1. How we call it? A voltage 1 plus B, A voltage 1, yes, plus B voltage 2 plus C voltage 3, right? That's the type of interpolation that we said we're going to do. Okay, of course, A and B and C have been computed before, and they were elements that we used to compute the R's, the Q's, the E's, and all this big mess. Yeah. Okay. Now we have, when we do this, now we know voltage of X and Y everywhere. So it's known now. Great. We have, now we are able, instead of putting this, we are able to put these distributions. We can plot it, we can see it, and we are all very happy. But that's not what we want. We want the electric field. More important is the electric field. E, which is a function of X and Y. And not only is a function of X and Y, E, which is a function of x and y, has two components. Has the component x, which is a function of x and y in direction x, plus the component y of x and y in direction y. And is going to be computed by E equals to minus the gradient of B. For 2 dimensions, this is going to give you minus d dx, b of x and y in direction x, minus d dy of b of x and y in direction y. Okay, that is at every point. But since we have done B has been a interpolation, and I'm gonna put here linear. When you take the gradient, which in the end is to take a derivative, it means that the electric field changes in steps. So in a particular region, it's a linear interpolation. Therefore, it's a constant. So you have that this is the voltage, right? So and let's put it like that better. It's something like this. This is the voltage. And you go here, this is your X, and this is your Y. So the electric field is going to be the derivative of these things. So since you have it by node, let's say you have the values here and here and here and here and here and here. These are the values that you have. The electric field now is going to be the slope. So this is voltage of X and Y. The electric field on X and Y is going to be the slope that we see in these places. So for the first region, let me bring the first region over here. For the first region here is the slope there. So it's a constant value here. Then for the next region, it's a slope that is smaller, so it's here. For the next region is an even smaller. For the next region is 0. For the next region is a negative value, a little negative. Then it's a little positive, and then it's more and more and more negative. So the electric field goes in steps like this. This is how you would see the electric field for a particular dimension. So the electric field doesn't look very good when you do only linear interpolation. So what do we do?
No, I mean, the plot should be reversed.
The plot should be reversed. You're right. Yeah, the plot should be reversed. Yeah. So the plot should be, this is a negative value, then it's less negative, and yeah, and then it's a positive and positive and positive and positive, and the plot should be reversed. Fayaz, you're sleeping. The only one.
No. I was thinking that how you're.
You've taken enough classes from me to know that I make a lot of mistakes. So that you need to follow and then repeat everything at home. Yeah, so I make a lot of mistakes. That's right. Yeah. Okay. So what if you want smoother electric field? What if this jump is not interesting for you? Any human, but only humans can do this. And maybe artificial intelligence can say, well, really, I can just put a line in between. And this is what the electric field looks like, right? This is the eyeballing, right? It just that's how it will be. I know that if it varies like that, nothing in physics varies like this, right? Unless there is a boundary, electric field will not jump. Electric field will be continuous. It will be nice. Remember, we have our boundary conditions for D. If there is no charges, there is no boundaries. The field, the normal and tangential fields are simply constant if you don't change either the field of the parameter or the permittivity of the medium. It just continues. All right. So what do we do if we want a better a better electric field? To get a better electric field, we do quadratic interpolation. Okay, now what you do is you have your triangle. Normally you would use these nodes only, but now you use additional nodes in the middle, right? And then that allows you to write a quadratic function. I'm not going to cover this. All programs have these things. When you have quadratic interpolation, you get a smoother electric field. You get a smoother electric field. Now it will be piecewise linear, right? Now, instead of being like this, it will be from this point to this point, connected with straight lines. Here, so if you have something that varies like that, and you have sufficiently wide, you're going to be like this, like that, like that. But you have, since you have a smooth electric field, it allows you to have a coarser discretization. So instead of having to do very fine, you can do less. You can have much bigger triangles. So normally you would do like this, right? We have done this. We have come here and use these triangles over here, these triangles over here, like this, boom, so far, for linear. When you do it for quadratic, you can still use the triangles, but you're going to get the same accuracy if your triangles are much bigger. So you will have fewer triangulars, fewer bosses, fewer things. Now, if you think it was a mess to do all this for the linear interpolation, you can imagine the complications that you're going to get into a quadratic approximation or a higher order interpolation. Now, people have done it, and commercial programs have the possibility of you to use higher order models. And they work. They sometimes give you more efficient solutions. So, and the price to pay is complication in the formulation and all that. But since we really don't program our own final elements, there are a few people who program final elements. I know a few researchers that have programmed their own final elements, but most of us just use the program. But we need to understand how the results come and how to do this. Any questions?
Gotcha. So for now, we're still focused on the electrostatics, which is using
Yeah.
potentials.
Is the scalar electric potential? Yes. Yeah. Next session, I will come with all the formulations for final elements from electric fields, magnetic fields, and at least two potentials, the scalar electric potential and the magnetic vector potential. Okay, those two are the most used. There are other potentials that if you have a magnetostatic problem, you can use a scalar magnetic potential. And normally, for completeness, there is something called the vector electric potential that is never used because it gives you the same dimension as the problem. So if your problem is 3 dimensions, the potential gives you 3 dimensions. If the problem is 2 dimensions, the potential gives you 2 dimensions. So you're not saving anything, right? So it's never used. But in theory, it exists. Yeah. But never use it. You will see that final elements will solve 3-dimensional problems directly, electrostatic or electric problems, always with the scalar electric potential. And most 3D problems and all 2D problems will always be solved if they are magnetic with the magnetic vector potential. We will see the advantages and disadvantages next time. But it takes at least an hour to go through all these things. No.
All of them are solved in potential ways.
Not necessarily. Well, not 3D problems. 3D problems, magnetic 3D problems, or magnetic 3D problems may be solved directly for fields. Yeah. Now, many programs, COMSOL in particular, don't really allow you to do a 2D problem with magnetic vector potentials if it goes vertical. So if it is flat, fine. If not, you have to do it by fields. They don't let you use a because they have no program it, the magnetic vector potential for 3D magnetic problems. Yeah, it will be clear next class. It will be very clear. Oh, I know why. You will say, oh yes, that's why it's no point. So for 2D problems, in particular, COMSOL doesn't let you specify the excitation other than coming from the plane. So you cannot have the excitation going up or down. It has to come in and out the plane that you are modeling in 2D, because they don't do it. I mean, they don't do the whole thing. They do whatever is more useful for the general public. You may have a problem, and probably you will rarely encounter a problem in which you need to put the excitation in a different way and still do a 2D problem. You will have to do a 3D problem. In 3D problem, they solve it anyway. You've seen it. You can excite whatever you want in 3D. Okay. All right. Question, Fayaz? No? But for now, I am done with the class for today. Questions out in Mexico?
Only one, Dr. De Leon. In the element function, I missed that. I missed why you didn't consider the permittivity and the area. You consider that is the same area of all the triangles and the permittivity is the same. That's why you didn't put it in the element function.
No,
Uh,
each, okay,
there,
here,
you're not including the 1/4 times the area and the permittivity. Is multiplied, no?
I see, where is it here? Where, here?
Mm,
Yeah, but not, each triangle it has a different area. So,
mhm.
whenever you
Each,
have, so this is per triangle. So
uh-huh,
you have a different, you will have a
area.
different matrix, a
You
different,
might have it.
yeah. Every one of these E's corresponds to a triangle, right? Triangle K. If you have to
Mhm,
triangle K plus one or triangle J, you have, it's a completely different E with the coordinates and the area
mhm.
of that particular triangle. I have not done anything with the permittivity here. I didn't take it out. I didn't consider it at all, right? It
Okay.
um, for the first time, I think we cannot, I cannot confuse more. It's already very confusing. So I
Mhm.
cannot confuse it more with variable permittivity.
Yeah, yeah.
But, but we can definitely build the permittivity. The permittivity, if you want to consider different permittivities, you have to do it through boundaries. So let's say different permittivities. So let's see the problem that we had before. And now you have two elements. Here it has epsilon 1,
Mhm.
and here you have epsilon 2. So you need to make sure that when you discretize, you have to open your triangles need to make sure you need to make sure that you have them yes that there is triangles at the boundaries, and that's why the programs will always it will always ask you to define solids or regions with the same material. You're going to have to put materials. So um, you have it here, right? You have to consider the fact that there is a boundary there, and you need to discretize up and below with different values. Yeah, and that needs to be included right here. Let's see what is the thing right here, right? So yeah, you multiply there. So and you solve this equation per regions. Okay.
Okay.
Yeah. We will do a few examples. We will do a few examples with this. Okay. I think that's it for today. If there are, I stay here if there are questions. If not, I am very hungry. Yeah.
Thank you, Dr. Leon.
Okay, there is a question here. So,
Well, the permittivities. So so yes, the mesh are different, like, they consider different triangles on different kind of
yeah.
permittivities. But the fields are constant, right?
No, the field is not going to be constant.
Field is not constant, it's continuous.
The field is continuous. No, no. The field may have a jump if there is a permittivity. The tangential component of the field is okay because you're not going to have a charge in the middle most times. But the um, normal, the normal component of the field will have a jump. Remember, dn1 is equals to dn2, assuming no charge, right? Okay, so you have epsilon 1, E normal 1, epsilon 2, E normal 2. So if you have E normal 1, you're going to have E2 by E1, E normal 2. So the field can come this way and at this point refract. The tangential component stays the same. The normal component magnifies or reduces.
There's
Yeah.
not really a problem that, when divide when have two different kinds of permittivities, the software always do the nodes, which is on the top of the triangle and the bottom of the triangle.
Mhm.
They try to on the same nodes and write that.
They need to share the same node, otherwise the model is disconnected. So
But the reason
in
there's
finite element, you need to model the universe.
Yes.
So no part can be with cannot be modeled. Everything needs to be modeled.
Yes.
So when you put two different things in contact, they need to share for continuity, they need to share the same nodes. They will enter differently in the matrix. The values will be different.
Okay. So same nodes need to make sure that the geometry is
Continuous.
okay.
Yeah.
Form, form assembly or form.
Speak a bit louder, please, because not even I can understand it.
There is an option for meshing in console, like form assembly or form something like that. So they say this thing to make sure that the nodes touch each other for different regions.
Yeah, this is very important. If you build something that is not continuous, it will give you an error.
No, the thing that if you like do the electric field or magnetic field is fine since everything is in union. But if you do it like I can't remember the word. If you do it assembly, it can still do, but there's an accuracy problem at the boundary. So it's not really so it's not necessary. It's not it doesn't really force you to have the same nodes at the boundary. But yeah,
I would doubt why you cannot have this. We need to have the same nodes at the boundary. Otherwise, all discretizations have to, every boundary needs to have the same common nodes on both sides.
okay.
I have never seen anything that has,
I can show you later.
okay.
Don't have a break. We can.
Yeah.
I can do
So
yeah.
we are going to stop this now and have lunch.
There, we should see the form union and form assembly
Yes.
thing in console.
Yeah, but when
Because-
you do assembly, the map nodes is not really mapped one to another.
In case of moving mesh, like this could be the thing we do the separate,
Yes.
but in form union.
So I
form-
that I don't know what the program would do.
Okay.
So let me stop the recording.
There is a YouTube video you can see.